And this is Lindsey.
Yeah, hi, I'm Lindsey. So we're both data engineers at Deliveroo. And the aim of our talk today is to give you an introduction to the Streams API, which is some functionality that Kafka offers, and just give you a bit of an insight of what can be done with that library and some of the lessons that we learned from implementing our own use case with that. So yeah, we both work for Deliveroo, and Deliveroo is a food delivery service. In case you haven't heard of us, I assume you have. We started 5 years ago, and from kind of proof of concept to now, we've grown really, really rapidly, and we're now operating in 13 different countries. What this means from a technical point of view is we're in the process of decomposing our monolith that was written in Rails into microservices so that our platform can be more easily scaled and extensible. We're using Kafka as our message bus between these services.
So our agenda is like I'm not sure this. So we're gonna introduce you to Streams API from Kafka through one of our use cases in data engineering team, which is some challenges we had with tracking the consumers, and then we're gonna walk you through how we solve it and what headaches we face with the Streams API. But before we're going with anything, how many people here know Kafka? How many use it in production? Awesome, so we have like good diversity.
Okay, fair split. So we'll aim to give a bit of context to people that don't know about Kafka. So Kafka runs as a cluster, and it stores streams of records into collections called topics. Each topic consists of a configurable number of partitions, and a partition is an ordered immutable sequence of records. A record consists of a key, a value, and a timestamp. When a record is written to a partition, it is assigned an offset, which is a sequential ID, and this is unique to the record within that partition. Topics can be read from a consumer group. Partitions are assigned to instances running in a consumer group. So in the first example, we've got consumer group 1. There's just one instance running, so both partitions are assigned to that one. In the second example, there are 2 instances running, so each instance has 1 partition each. And this is how Kafka scales consumer groups horizontally. Kafka cluster keeps track of the latest offset read from the consumer group by each partition. So if one of these instances goes out of service, another instance can restart and just start again at the position in the stream. So that's how it handles fault tolerance. And just a quick note, the word record, we might refer to that as a message or event later in this talk, but all of those 3 words mean the same thing. So an example consumer looks something like this. You need 4 properties, the minimum of 4 properties for your configuration. The first is a bootstrap server, and this is just the address of the Kafka server. Second one is the group ID. This is the unique identifier for your application, and this is what Kafka uses to manage the offsets. And then a key and value deserializer, and this is just the type for being able to read the record. Then you can instantiate a consumer with your configuration, and then you can say subscribe and pass in a list of topics that you want to subscribe to. And finally, you can write a poll loop, and this is where you implement your business logic for actually processing the data in your consumer. Now, imagine we switch that on and we want to see what's happening. Kafka comes with some shell scripts out of the box. So if we execute Kafka consumer groups and pass in our group ID and the describe flag, we can see some information that looks like this. We can see that our current offset for each partition for this topic. We can also see the consumer ID. This is the identifier of the actual instance that's in service. And then finally, we have some information called a client ID. Now, a client ID is a unique identifier for an application, which sounds a lot like a group ID. A group ID is also a unique identifier on the application, but both of these things fulfill different roles on Kafka. So a group ID is what Kafka uses for offset management. A client ID is used, it's what's written to the logs for kind of monitoring what's happening with your consumer if you want to debug it. And it's also what's used for quota management, if you want to implement quotas on your consumer as well. So a couple of constraints that don't really get enforced. So you don't have to set a client ID to get a to get a consumer up and running. But if you don't, libraries will provide a default. So in this case, we saw that consumer 1 was the value for client ID because I hadn't explicitly set it, and that's the default value for this Scala consumer library. This is kind of a problem for us if we want to run in a large organization like we do, because if our users don't set a client ID, library default might be used, and in that way we wouldn't necessarily get a unique identifier for each consumer group, and it'd be hard to track them in the logs. Another thing is that we can't reuse a group ID across applications. Kafka will see that as a scaling action. So if a new application used the same group ID that was already in service in production, that would cause the data to get shared across applications. So we want to make sure that any new consumer group wouldn't reuse a group ID that's actually already in service. So, problems we're trying to solve. How can we actually track what configuration settings are being used in our consumers across our organization? And kind of tangentially to this, how do we know what applications are actually live right now? So if we were faced with a production issue on the Kafka cluster that we knew were affecting consumers, we'd want to be able to know really quickly actually who exactly is depending on us and be able to kind of navigate through to some logs and make sure that we can understand the behavior between the Kafka cluster and kind of how the consumers are behaving. So this led us to build a tool. We've called it Ruhu. This gives us up-to-date information about all of our consumer groups that are actually in service right now, and we display the group ID and the client ID. We flag here any consumer groups that are using the default clients IDs that we know about from libraries, and here you can click through and you can navigate to logs if you want to check the behavior of how all of our consumers are actually running in production. This has been a really helpful tool for us for kind of managing, administering Kafka across the organization.
So if Kafka can actually manage the consumer offset, this means Kafka somewhere is actually stores this information about where's the current offset for each consumer, and more important, what's the configuration for this consumer. And this is the famous internal topic they have in Kafka called consumer offset. But the problem with this topic is this topic has two different data. One, it can tell you what's the current offset, which is something looks like this. It's a record with a key as a group ID, a topic name, and the partition, and the value is where you are. And when was the last time you commit this offset? The other data is the group metadata, which is the minimum configuration about the consumer. So the key here is different. The key here is just a group ID, and the value is totally different value because the value is a metadata about what the consumer ID is, the ID of this consumer, was the client ID, which is surprise for us, was really hidden deep inside this model. It's not they don't deal with the client ID as a first-class citizen, so we can grab it easily to build our dashboard. So this kind of problem with the consumer offset will make the code more complicated and need to be dealt with the record in two different ways. So the idea was we have a consumer offset which has some binary data with two schema, one for offset and one for group metadata, and we need somehow we move to a time windowing, which is when this consumer was live, and an active group, which is our model that combines the offset and group metadata in a different format, so we can use it for the dashboard, store it somewhere, and then query it back to build our dashboard. To do this, we decided to use a Streams API because the other alternative that we get to consume and store and manage a database and stuff like this by ourselves. And using Stream API was the easiest way to start this project. So, how Kafka Streams API is actually working? So you have something like a topic, which is consumer offset, and you have your application have multiple instances. The Stream API is just a jar inside your instance, and that's it. And it listens to the topic, it assigns to some partition, so in instance 1 has partition 0 and 1, do all the streaming processing on it, and what you need, it will have it in this instance, and the other instance will deal with partition 2 and 3. So if you're looking for a real-time stream processing, Stream API is a good fit. It's for applications that are trying to consume and be reduced back to Kafka, so you didn't need to deal with a low-level 2 libraries. You just deal with one library and focus more on your business logic instead. It supports stateless and stateful processing, so you can do the normal things like map and flat map. At the same time, you can do an aggregation and join and stuff like this. It's a scalable and fault tolerance, and we're going to talk about the fault tolerance in more details later. And there's 2 ways to deal with Kafka streams. It's either with a high level, which is called a DSL, this is what we can show you today, or a low level, which this is really hard to do because you need to know exactly what you're doing. And the last thing, as I said, is a jar, so it's available for Java and Scala for now only. There is a small rubber, a thin rubber from Lightbend called Kafka Streams Scala, which makes the code looks much prettier and more like a Scala way, more than if you use the Java one. We started with the Java and we decided to switch to the Lightbend like after 2 days or something.
So this here is an outline of the computations that we're going to do for our transformations. So the Kafka Streams DSL that we're using for this library, what you do is you specify an input topic, and then you can compose transformations on the stream. So we don't use every single method available in this library, but actually we touch upon quite a lot of the main abstractions just through solving this one problem. So the first thing we're going to do is split our input stream into the 2 different types of data that we know we have, and have 2 streams to then manipulate. And then taking the top branch, we're going to perform a map and a filter so that we can transform the data into the type we want. And then on the bottom branch, with the group metadata, we're going to perform an aggregate on that so we can get the latest group metadata that we know about. And then finally, once we have both of these 2 sort of streams with the group ID both as the key, we can join this back to our own stream where we're using the group ID as a key and our Scala defined model active group. And this group has both types of data that we care about all in one record, so we can manipulate the stream like that for using the Streams API. So what does this look like in code? So the first concept that you come across in the Scala Streams API is something called a KStream. We can think of this as an unbounded sequence of structured data, and this is what we can perform our computations on. So we can instantiate such thing by calling builder.stream and passing in our input topic. We don't have to explicitly ask for data with this. As new data is written to our topic, our processing topology will just get executed without having to sort of ask for data, unlike the consumer above. So the first method that we use is a branch. Branch takes in a list of predicates and produces an array of streams. In our case, what we're going to do is deserialize the key of our record and check to see whether it is an offset type, and if so, true, and if not, we return false. So that's the first predicate, and then the second predicate is group metadata, is just the negation of is offset, because we know there's just 2 types of data here. So now we've got our 2 streams. So taking the offset stream, what we do is a map on our binary data. We have binary for both the key and the value, and then we can pull out the group ID, and then we produce our own Scala model, which is the offset details. And then finally, we filter out whether it's committed in the last 10 minutes, because we only really care about recent data for our use case. Just a note, the map here, because we're mapping over the key to use for a join later, this is going to actually cause the Kafka cluster to create a repartitions topic. We'll come back to that later.
So the next thing is actually try to get the latest data, like what's the latest consumer right now for the metadata branch. So in Kafka, this latest definition of the data is called table. And they call it table because this will be a key and value thing at the end. You're never going to see the same key twice. You will never going to see the same group twice with different data, with different values. So it's just the same idea about table in database, it's the same idea in KTable. The only way you can get a KTable in Kafka is either by an aggregate or a reduced stream. So you had a stream which contains the whole history of your records, and you do an aggregate to get the latest of this one. So imagine that you have a stream, a group metadata stream, which has a group 1 with metadata version 1, and then you have a new group called group 2 with the metadata version 1 for this group 2. And then group 1 is either there is a new consumer join or a consumer left, and the version of the metadata become 2. The version 2 is the same metadata. If you do an aggregate, it will end up with a table where the group 1 has the latest value, which is metadata version 2, and group 2 has the latest value, which was the metadata value 1. So to achieve the aggregate, you grab your stream, which is in our case is the group metadata KStream. First thing is we don't need to deal with binary data all of the time, so we need to map it first. So we will map the binary data to be a group ID and client details, which is client details here at the end. It just tries to restructure the data to treat the client ID as a first-class citizen, not deeply hidden inside the consumer. And then we're gonna do a group by key, and group by key is important because an aggregation in the stream is actually an aggregate by key. So you need first to group them by key first, so you can do an aggregate by key. And in the aggregation, it's so simple. Just take an initializer. In our case, we define the initializer. It's just a client details with everything is empty. And the aggregator body, which take a key, a value, an aggregator, and you do your aggregation, and this will run and give you a key table of a group ID and client details. The first thing here is the group by key has a big gap. And this big gap because the group by key doesn't know how to serialize this new type of data, which is called a group ID and client details. Kafka doesn't know how to serialize this. So to do this, you will need to define a serialize, which is your own serializer. There is the library come by some built-in serialization, which is a string and double bytes like the normal stuff. But if you want to customize your own serialization, you will need to override the serialization and deserialization interface, which is the first object here is applied in serialize, which is just an overriding. And at the end, you will say that you won't need to create the serialize itself, which is a serialize or serialize from a serializer and deserializer. And this will give you a serialize you can use later for the group by key. So group by key now can be like this. A serialize with a serialize for string, because group ID is just a string, and the custom one we define for the value. This code is work fine. The only last trick is aggregation has a side effect too. So because it's a stateful and it needs reshuffling, it has a repartition topic. We got to talk in more details about why this is side effect and why it's more pain later. So now we have a key table, which we just reduced, and we have the stream we had earlier from the offsets. We just need to join them, combine them together to have the active group metadata we define. So in the Kafka stream, they provide the join between table and stream, or a stream and a stream, or table and table. So this just should be a piece of cake. You just have your stream, which is offset commit for the last 10 minutes, joined by the table, which is the last group metadata, and the join body, which just combines them in active group. An active group just a simple model have a client details and offset object. The only trick that join as a group by key, join doesn't know how to serialization too. So to serialize and deserialize, you will need to define a join serialization, which takes the key, which is the same key for both the stream and the table, which is string, and it takes the serialize for the first thing, which in our case is the stream. This is the consumer offset details, and the second value, which is the value from the key table, is the client details serialize for this one. And this will give us a key stream for a group, an active group.
So now that we've manipulated our topic into a kind of format that we want to reason about, the next thing we're going to do is make use of another part of the library, which is the interactive queries. So for this, we're going to implement a window by time, so that we can group all of our events by the time that they occurred. And this is what's telling us what's active, what consumer groups are actually active right now. And then we're going to make use of a state store to query this data back for our dashboard. So the windowing operation in Kafka gives us the ability to group events by event time if they're grouped by key. So if we have our kind of flow of data, these would all get put into a specific time interval and also grouped by their group ID. So the code for this looks like something like this. So we take our join stream, we group by key. Again, we need to pass in a survey for this. And we can call the window by operation and pass in windows of, here the time unit is milliseconds, so the 60,000 relates to 1 minute. And 1 minute is really enough granularity that we need for deciding whether a consumer is online for us or not. And then we can make use of the state store in the Streams API. So the state store gives us the ability to store the data that we've processed and query this back. It makes use of local state on the instance itself. And by default, it uses RocksDB, but this is configurable and you can use a different query engine if you choose. So we can see this state store is really a materialized view of the data. Kafka is maintaining a changelog under the hood of all updates to the events, and that's so that a local instance store can be rebuilt in the event of a crash. Now, if we happen to be running across 2 instances, then our state store is just going to store the data for the partitions which the Streams API was actually assigned to for that instance. And that means that each individual store would only get a subset of the data. So if you're interested in running across multiple instances and you need your full data set, then you can implement an RPC layer, for example, REST. And this means the instances can find which other instances are in service and potentially remote query them to get the full data set. Because we're running this on an internal tool, we can run this on one instance, so we actually haven't implemented this in our code, but it is an option. So the code for this looks like something like this. So because we've got this windowed stream, in order to query it, we need to get this into something where there is just one record for each key in each time window, so we can use the reduce or the aggregate function. In this case, we're using reduce, and we're arbitrarily choosing a record here. That's because we know we've got the latest group metadata from the computations previous, and the actual granularity of kind of the offset information isn't super important to us here, so we're just choosing a record. And then we can use materialize as, pass in, serialized as, we pass in the as type parameters our key and their value, and then the type of our store, and we can give it a handle for us to be able to call that later. And again, we need a key and value survey. So then to query this, we can call streams.store, pass in the name and the type of the store, and we can call all to get a whole list of records. This is what we use for our dashboard, and then we do a little bit more manipulation just to pull out the last time we heard from a group by time window. We can also do a fetch all and pass in a window of time, and that will just bring you back the records relating to that time window. We use that if you care about kind of historical active groups. You can look at that on the UI. And an example record looks something like this. So it will have the group ID prefixed and then the time window, and finally active group as the value.
So far, System API just have like 4 main concepts like stream, a table, a serializer and deserializer, and a set store. But actually under the hood, this is a beast running in your machine. And to understand what's actually this running, you can ask the stream to describe all the topology that it's running behind the scene. And to do this, you get your builder, which is just the normal builder to build the stream, and you ask it to describe itself. And this will give you something ugly like this, which says that you have 2 topology. The first one is reading from a topic called a consumer offset. It did branches or something, and then try to have 2 branch. The branch gets children, and blah, blah, blah. It looks ugly, but to make it more breathier, you can use an open source tool called Kafka Stream visualization. This one will draw for you this. It just copy and paste the same string you get from the topology. Give it to this tool, it will give you a pretty version. And if you see here, when you see a rectangle, this is description for a topic in this graph. And here's the first topic we have is the consumer offset. This is our main offset, our main topic, the one we're reading from. We know this guy. We try to stream from it. We try to branch. We end with 2. We did some mapping, a filter on this one, and we did aggregation on the other. We know this. What we don't know is that these two rectangles is 2 topics had been created behind the scene, and you didn't have any, you have like a small control over them. This too is because the repartitioning. We said that the map and aggregation decide to create a side effect, which is the repartition topic. This is what happens every time you touch a key. So if you're doing a map, flat map, a selected key, this means you have a potential of changing the key. Kafka will mark the whole stream as a repartition. And at the end of dealing with the stream, they will have a topic or a repartition topic. And the same, the aggregation needs a reshuffling for the data, so it has a repartition too. So this called an internal topic called a repartition topic. This is behind the scene. Kafka do it for you. And your app will keep consuming from this too. So right now your app is consuming from a consumer offset, a 2 repartition topic, not only one. And as I said, we have 2 subtopologies. This was the first one. The second one is this. So you had this repartition, you did an aggregation, and the other side you did a join, a reduce, and the store is just looks like a database thing. And this is our output. This is the one we define the active group state store. What we didn't define is this. We didn't define another state store. This is because the aggregation is a stateful, and Kafka needs to keep a track of the stateful of this one. So they will build a state store behind the scene in your instance. This means there is more memory taken from your instance just to hold this data. So this is a side effect on your application. There is another side effect which is related to the fault tolerance. What Kafka tried to do is what happens if this instance had crashed? How the state store will going to rebuild again? They stored all of this in something called a changelog topic. And a changelog topic is holding all the changes that happened for an aggregation, or a changelog happened for the state store. So if you had a crash, your machine come back, it will try to build the state store from this changelog topic. So this means that now, how many side effects topic we end up with? 2 repartition and 2 changelog. We end up with 4 had been created in our cluster. So this headache can be manageable. It's not avoidable. It's like you can just tell Kafka don't create repartition, don't create a changelog. Not really that easy. What you can do is little bit ask Kafka nicely to clean it up. So you can set the retention and the cleanup configuration when you build your configuration for the stream. So you can say the topic retention milliseconds. In our case, we said it's hour, and please make the cleanup policy delete. So every hour, Kafka will go through these topics, see if no one touches this data for the last hour, they will delete these records. This will end up with less data in your cluster, but still you have topics in your cluster. The other thing, avoid map. Don't do mapping. Instead, map on values and flat map values, so you don't touch the keys at all. In our case, this was impossible because the keys wasn't the same format, so we needed to actually make both of them in the same format, so we had no choice in this. So this was the headache that you can manage. There is other headaches you can't, which how these internal topics had been created. So every time you create a topic in Kafka, you want to tell Kafka how many partitions this topic will be and how many replicas. This is the minimum for creating any topic. So how many partitions this topics has? So we know that by default, the consumer offset from Kafka, this is 50 partition. And because this 2 partition topic had been created from this one, it will inherit the parent. So both of them is 15. And the changelog is inheritance 2, both of them is 15. So only our application had been created 200 partition extra in our Kafka cluster. So this is an overload for Kafka cluster. The recommendation from Confluent is 2,000 partition per node in your Kafka cluster. We just took 200 of them. The other thing is the administration. If this app, we decide to shut down the whole app, we don't use it anymore, Kafka is not going to do a garbage collection and delete this topic. This topic will stay there. And this means that every time an application uses the Stream API go down, they will need to notify the data engineering team to delete the topic manually for them. The other thing, there is no any guarantee that these partitions, 50 is actually an even in matter of how many messages inside each one. You could end up that your filtration had most of the data in only 2 or 3 partitions, and the rest of the partition is either empty or has less messages. This has 2 problems. First, in your app, if your app is scaling, this means the instance that holding the partitions that has more data will have more pressure on it to deal with more data. This will affect the performance of your application. The other thing, from Kafka cluster point of view, this means that we have a topic, has few partition, has more pressure on them to pull data from them. There is no unequal distribution for the pressure for dealing with the messages. So to solve this, you maybe want to go low level and don't use the Stream DCL API. There is the other one, which is this is the low level Stream library called Stream Processor API, which is what used behind the scene in the Kafka Stream API, the DCL one. Which means you need to do more work, and actually you need to know what you're doing, because you will be replicating what the DCL doing in some matter. So you will need to know what's the problem you're trying to avoid with the DCL, and how you can implement this and avoid this with the processor API. It's more work, it's more harder, it's more complicated. So our sources is this app we just showed you is actually an open source and Deliveroo dashboard. If you're interested in some external resources, there is a good one about how Kafka looking in the consumer offset topic, and there is why Kafka Stream didn't work. For us, this is written by the same guy who actually inspires the Lightbend library that had been built. It's a series of blogs from Sri. He showing all the problems with Stream APIs and why he didn't go with it for one of his applications. And the other thing is the Stream visualization tool that showing you what's happening behind the scene in Kafka Streams.
So just to end here, the Streams API is a really powerful library for both processing and querying data in real time in a really highly flexible way. It is really important though to understand what the effects of your implementation might have on the cluster and how state is managed on the application, so that you can make sensible configuration choices based on your requirements for scalability and fault tolerance depending on your use case. Kafka is working really well for us as a message bus between services. And at the moment, we're using the Streams API for an internal tool, but we can perceive use cases down the line where maybe our Kafka cluster will be used to maintain common state derivations of our data, as well as passing data between services. That's everything from us this evening. Thank you very much for your attention. I hope you got